So I would like to discuss today mixed stochastic-analytical Brownian simulation. So this is a class about simulation, how to generate Brownian trajectory in an infinite domain. And the motivation for these questions comes from a question or several questions in biology, which is the following. Suppose we have a cell with a receptor located on the surface, so those are the receptors. So it's one of them, and suppose there is a source somewhere, a source that generates particles, like Brownian particle that I will draw now in red. So you have a Brownian trajectories, whatever it looks like. You can have another one. And so you are interested in the question, first of all, of simulating these trajectories so that you can calculate the flux to each receptor. So let's suppose we call the receptor 1, 2, and 3. So you are interested in, for example, calculating for a certain amount of time. So suppose this is time, and you are looking at the number of particles or the ratio of number of particles arriving at receptor 1. So you have here the number of particles, let's say at receptor 1, or you can also calculate any ratio of or quantity of interest. This is the ratio of number of particles arriving at 1 compared to the one arriving at 2, but you can also take, let's say, to have it normalized to a probability, you can take the sum of R1 plus R2. And so you're interested in what is this ratio, calculating this ratio. For example, you can sample over a certain window of time, and you say during this window of time, what is the amount of receptors or this ratio that you're going to obtain. If you're at steady state, of course, this is not that important because this is constant. If you're not at steady state, then the sampling time is important. So how to do such a simulation? Well, you can do it, first of all, in a very naive manner. So what is the naive approach? Then you have a source and you generate trajectories that can go to infinity, because we know that in dimension 2, although the Brownian motion has the recurrent property that it comes to any of the point an infinite number of time, it makes a very long excursion. So if you are interested in calculating the flux through, let's say, this receptor, so you can have trajectory that can go very quickly, but some that are going to make very long excursion. And so we know that the mean first passage time to this question is going to be infinite. So if you generate trajectory in a very naive approach, then we are going to spend time, or the computer is going to spend time generating trajectories, and this will eat all the time, all the simulation time. So a second approach, which we can call it less naive, is to say, well, instead of doing the simulation in the infinite domain, so this is in the infinite domain, no boundary here, then we can repeat the same simulation and add a sort of artificial boundary, saying that if we have a trajectory generated here at point S, and if the trajectory is moving, when the trajectory hits this arbitrary boundary, then the trajectory is removed at this point. So of course we are making here some, this could include it could induce mistakes, because the trajectory then, when it moves, it would eventually come back here and resume its trajectory inside the domain. So then this says that we can make with this approximation some mistakes, but the idea is that as the radius here of the ball tends to infinity, this mistakes tends to 0, and then you recover what you would get if you would have done these naive simulations that we discussed in part 1. So what I would like to introduce today is a different approach, which we are going to call 3. And this is about mixed simulation, stochastic simulation, and analytical one. So this is this mixed approach. All right. So what is this mixed approach? Well, the mixed approach consists, so let me erase, or I will just use this, I will erase this part here. So to describe this mixed approach, again, suppose we have a source located here. It generates particles. We have a domain where you are interested in how the particles that are generated are going to sample this domain. So you have trajectories, and in principle they should arrive here to a place of interest. Now, instead of generating this entire trajectory here, the idea of the method is to say that you are only interested in simulating those trajectories inside a neighborhood here in red of the domain of interest. So we are here, we are having here an artificial boundary, and we propose to do the simulation as follows. First, we don't generate the trajectory from in this space, from S to this boundary. The idea would be to position the, according to the probability of hitting this domain in red, to position at some place with a certain probability P that we're going to see how to calculate it, to position the trajectory, and then the trajectory would start from this position, and it can be reflected, it can be absorbed, and then you can count this event as 1 in your statistics, or the trajectory can be reflected and reach the boundary, or we can have a secure boundary and move a little bit outside, but let's, for this example, suppose that the trajectory is going to be removed when it hit here this boundary at a point, let's call it P exit. So at this point, the trajectory is removed. So with this method, we are not going to simulate and waste time generating all of these trajectories here. Instead, we start from the red boundary that we have shown here. So we start with this boundary here and simulate trajectory inside. So now I would like to summarize through the following graphics. So suppose we start at a position here, which is shown here with the marker with the red spot. You use the Green's function to see where the trajectory is going to be generated here on the artificial disk here. You generate then the trajectory. So here we assume that we have 2 absorbing windows, and the rest of the rest here of the boundary is reflecting. So when a trajectory moves, it can either, of course, arrive to the window or be reflected. And here this is an example where the trajectory started at this point, it arrives to the window, or the trajectory is not touching here one of the two red windows, and then it's going to be here removed, and we can restart the simulation and calculate the probability of the initial position and restart the simulation, and then generate the statistics that we are interested in. So this is an example where the points are located on half a space on this line. Here the points are located on a disk, and there is also an interesting case where the disk here is located in a narrow strip, which is described here. And again, so if we start at the initial position here, we don't simulate the trajectory until this line here in black. Then we need to calculate the probability where the point is going to be released, and we can then generate the Brownian trajectories. Here's an example where it arrives to the window, and here it is an example where we have another artificial in this dot line boundary, where if a trajectory hit this line, then we stop the trajectory and restart the simulation at this artificial boundary, which is the one where trajectory starts. So what is the problem, the mathematical problem we are solving here? So let me describe this. In principle, we are solving at steady state the probability, which is solution of Laplacian P equals 0 or equals delta Dirac at position, let's say position Q, where the trajectory are starting. Let's call it position here Q, or here Q. Then we have dPdN equals 0 on the reflecting part of the boundary, and P equals 0 on this absorbing window. So if we have, for example, two absorbing windows, then we have d omega 1 and d omega 2. So by calculating these statistics, we are actually estimating the probability, so which can be calculated as follows. So what is the probability to be absorbed? Probability to be absorbed at one window. If we have, for example, 2, but if you have n, this is the same calculation. This probability P1 is equal to the flux dPdN on the window 1 divided by the sum of the fluxes on each window. So this is ds, and this is dPdN on window 1 plus dPdN on window 2. Okay, so this is the problem we are approaching by this stochastic simulation. We are estimating this probability. It's called the splitting probability. All right, so this is called the splitting probability. Splitting probability. Okay, so for this, let me explain now how do we calculate the Green's function. So if we start from a point where you have the source, let's say to a disk where you have the windows, then we need to introduce this artificial boundary here that we have discussed before. So this is called the artificial boundary. So if we want to avoid the simulation outside this boundary and calculate, we need to calculate where to start. So where the particle should start here, where the Brownian particle should start. So to answer this question, we can use what we have seen in previous classes, which is the exit probability, which is solution of Laplacian P equals minus delta Dirac at position S. But now we need to give absorbing boundary condition on this surface, let's call it sigma, on sigma. And we know that the probability that the particle will be located when it starts at S is going to end up at, let's say, position y plus dy or dsy on sigma. So this is on sigma. Condition that it started at 0 at position S. This is precisely the flux, which is again dpdn, solution of this equation, and you have to normalize it, integrated over sigma. Okay, and so this will tell us what is the probability to position the particle initially in this little box around the position y of surface, let's say dsy. So this can be calculated using the Green's function. And for example, here in dimension 2, so if we are in dimension 2 and we would like to calculate the solution of problem star, this is the classical Green's function, which we have seen in the previous class about Green's function. Gx of y is equal to minus 1 divided by 2 pi log of x minus y divided, so if we have here a disk, let's call this disk of radius capital R, then we have x minus r square divided by y square y. So this is the classical inversion, multiply by y divided by r. So this is in dimension 2, so x and y here could be seen as complex coordinate. And now we need to calculate the derivative. So if we want to calculate and have an estimation of p, we need to calculate dgdn, the normal calculated on the position on the disk, on sigma. So if we use the coordinate r, theta, and theta prime, right? So what does it mean? What is this coordinate system? So r and theta is, for example, the coordinate here of this point of r of S. And theta prime is the coordinate here of the point y. Then the derivative is going to be equal to 1 over 2 pi. 1 over 2 pi. And then we have r squared minus capital R squared divided by r squared minus 2r little r cosine theta minus theta prime and then plus r squared. So plus r squared. And this can be also calculated, for example, if instead of having the disk here in the entire plane, we have, let's say, 2 windows located in half a plane, and then the artificial boundary, which I'm going to draw now in green, would be just half the let me do it in so this will be half the plane, half a disk would be the place to let me show it using here. So this will be the place where we would have to calculate the artificial position of the boundary. So next, I would like to summarize what we have seen here. So basically, the summary of the method is we need to calculate or to compute first the Green's function for the domain of interest. So sometimes it is possible, sometimes it is much harder. I will refer to the in the publication to the case of the narrow band, where we have a band here, and the windows are located here, the absorbing window, and the source is here. So then we have seen that the second interesting step of the domain is to calculate or to generate the trajectories. So where do you generate the trajectories? You have here this artificial boundary. You start at this position, you generate the trajectories here in yellow until they arrive. And then why you are doing this is to estimate or to compute the different statistics, the numbers of particles arriving in here, let's say at Windows 1, or the one arriving at Windows 2. And you can then vary the position of the windows. So what is then the type of result you can expect from this? So suppose you are interested, you start at the position x0, and then we vary the position of the source. Now the question is, what is going to be the splitting probability? That is the number of particles arriving, let's say, at 1 compared to 2, as the position is varying. So when, of course, theta, the angle is 0, the probability to hit, if they are positioned exactly with the symmetry here according to this line here, this is a symmetry line, then of course the probability should be 1/2. But then as the position move here, the theta move towards pi/2, then we should have, of course, the probability to hit the first one compared to the other the probability should be increased. So here the probability P2 is probability to hit P2 before P1. So in here the probability is obviously going to 0. And when we move to the other direction, the probability to hit 2 first is converging toward 1. The interesting question is how this depends on the initial distance, which is L here, on the source, compared to 0. And of course, as L is increasing, you can see that for L very large here, the difference is not very much between the probability to reach one or the other, compared to the situation where, of course, they are very close. And this is interesting because we were asking how, in the context of cellular biology, you see, if you have a source somewhere, and if, again, a cell has to decide where the source is, and this is the first step of this process, is to look if the cell has receptors, is to compare, in some sense, the fluxes on the left compared to the fluxes on the right. And so how this fluxes will depend on the initial lengths here. And so obviously from this example, what we have seen here is that a few L, that is a few size here, basically if you are, let's call it R, after L, let's say bigger than a few times R, let's say 5 to 10, then this difference between left and right is quite small. So this is another example where, again, the particles are released at position x0. We apply the algorithm of the method we describe. We calculate from the Green's function the initial position. Then we generate trajectories from that initial position. The trajectory can either be removed if it escapes this radius, and then it starts again until the trajectory hit one of the windows and contribute to the statistics. And so again, we looked at what happened when we, for example, varied here the angle. So suppose the first angle, theta1 here, is fixed, and theta2 is varying here in this axis, in the x-axis. And again, you can see how the splitting probability changes, how it decays as a function of the angle. So you can see here the different results of the decay. Sorry. So you can see one example here. This is an example where the receptor is positioned perpendicularly, or when the receptor is located in the opposite direction. So what we did with all of this is to ask the question about triangulation. So let me explain quickly, and this will probably be the goal of another class, to ask and to discuss in specifically what how do we triangulate, how the cell can triangulate the position of a source, the position of the source. So here is the question. Suppose you have a source somewhere, and now you can calculate the flux at receptor 1, 2, and 3. Can you, from these fluxes, can you recover, or can you find where the source is located? So of course, if you have only 2 receptors here, you see, if you have a source located exactly symmetrically, so wherever the source will come from, the probability to hit one or the second one is going to be the same. So basically with only 2 clusters or 2 receptors, you cannot triangulate, because there will be one line of degeneracy, which is the manifold, where you can find your the source. But with 3 points, you can actually define and recover the location. And so this is what is shown in this example here. In here, what we did is we added a little jitter to the source. So suppose the probability is probability 1 plus minus eta, where eta is something like a 0. Let's say 0.5, like 5% fluctuations. What is the error you are making on the location of the source? So this is given here in the region 2, or another example is in region 1. And again, I'll discuss this more specifically. What is the mathematical analysis that we need using the calculation of the Green's function, the explicit calculation that can be done using the method of match asymptotics. But what we wanted to discuss here, what I wanted to show, is to to see that region 1 and 2 are very different. And so the fluctuation of the position of the source depends really on the angle compared to these 1, 2, and 3 windows. And so finally, this is an example where we can use the redundancy of having 1, 2, 3, 4, and 5 receptors. And so the calculation so that we have an intersection of many lines, and this intersection can reduce the uncertainty that you can get if you have fluctuations. This I will do a specific class on this triangulation problem. So finally, I would like to discuss what happened when you do the same, you want to address the same question in a narrow band. That is, again, suppose you start at position x0. Now you generate trajectory, as we have seen at the beginning, at this interface. The trajectory are generated, so you have Brownian trajectories here. They can either be hitting this boundary again, and the simulation resumes somewhere until you get your statistics. And here what we have added another artificial boundary here so that the trajectory are not lost in the other direction. And so why we did this simulation was to evaluate the role of a narrow band of size here A. And what happened when A is small, which means that it will be a little bit bigger than the radius, or twice the radius here of the ball, so that you have here a narrow passage. And what would be the goal of this narrow passage for the statistics? Well, what we have found here is that so this is the splitting probability. That is the probability to hit 1, which, let's call it, this is 1, and this is the whole number 2, or maybe this is the opposite here. It's unimportant. So what we have seen is that this probability varied. So for example, let's look at the case where here you have the first window located at theta 1 equals pi. So you can see the effect here of reducing A. So the probability starts at 1/2 when they are both located at the same place. This is with theta 2 equals theta 1 equals 0. And then it starts to decay. And the decay is very significant when A starts to be very small. And this persists, and this is what we are seeing here. This is persistent with very long position, very distant position of the source, which is L here. And so this is very interesting because it says that in confined domain, so if you have a cell in a confined domain with 2 windows, one here and the other here, and the band is very narrow, then suddenly you can start, the system can differentiate a source even if it is located at a distance very far away, let's say 100 times or more than the position, than let's say the radius of the cell. And the reason is due to these narrow passages here, because then this will create a very large disproportion of trajectory that could pass here before the one that that are going to be directly absorbed at hole number 1. So this is important because we saw that for gross cone or any of this cell that has to grow in a very confined environment, confinement can actually help in sensing molecules or Q's which are located far away. Okay, I will now stop here this class and refer to this following article for the exact calculation for the mixed analytical stochastic simulation method. The calculation we are doing in this article, we are giving the exact calculation for the Green's function in a band. So if you have a band, and again, so if you start at position S and you are interested in estimating the Green's function to know where you are going to give the position of the initial particle when the ball is located here. So this can be calculated using the classical Green's function solution. So this is Laplacian G equals delta of S. We have to give reflecting boundary condition both at the top and at the bottom of the band, and zero absorbing boundary condition here on this artificial boundary. And this can be done using an expansion on the cosine, because you can use the band and having many copies. So I'm not going to do it in here. I refer to this publication for the method and the exact calculation of the Green's function that you need in order to implement the method. And finally, I'll give the classical reference to the book of Schulz about theory and application of stochastic processes for what concerns the classical property of Brownian motion. Thank you.